Okay, here we are with another Mr. Weis solves an old AP problem. This time we're doing 2008, number 1, pretty old problem. The first few problems on the AP exam are calculator problems, so this is going to be one of those. I'll do my best to show you some of the calculator buttons that I hit when I actually go to solve this problem. So what's the setup for the problem? In almost all of this problem we're going to be using the following picture. So we have these two functions. On the top is this function I've drawn with the black marker, which is f of x equals sine of pi x. And on the bottom in this sort of teal marker is g of x equals x cubed minus 4x. So what do they want us to do? In part A, our goal is to find the area of the region bounded by these two curves. So in part A, we are simply trying to find this region R, which is all of this stuff right here. Okay, so what I like to do when I'm asked to find the area between two curves or volumes of revolution or literally any of these things, what I like to do is start by thinking about what it would look like if I were to do a Riemann sum of this. I'm not actually going to do it, but I'd like to see what would one of the rectangles look like if I were to do a Riemann sum, because this helps me to figure out what the integral ends up needing to be. So the way I do that is I'm going to pick a random x value over the region that I'm interested in, and I see that x seems to range from 0 to 2. And if I happen to pick my x over here, the rectangle that I would make that would be used to help me find the area of this region would be the rectangle that looks something like this. And the height of that rectangle would end up being the top function, which is sine of pi x, minus the bottom function. Now, of course, if I had picked an x over here, the rectangle is going to look a little bit different. But actually, it turns out it's the same sort of principle, that at this x, the rectangle that I would be computing the area of would be right there. And I see that I have the same top and the same bottom function in either case. So therefore, the area of region R can be computed as the integral. What do I think about what x's I was allowed to choose when I draw my little rectangles? I could have picked any x from 0 up to 2, and then I think about what the height of my box would have been. The width is going to be the dx that pops out at the end. So the height of my box ends up being the top function, which is sine of pi x, minus the bottom function, which is x cubed minus 4x. And then, like I said, the width of the box ends up being delta x, which becomes a dx when we take the limit of the sums of all of those things. So this is the integral that I'm going to compute, and I'm going to end up using my calculator to do so. So this is under Math 9, I believe. And Math 9 is going to ask all of the important information. So we're going from 0 to 2. I'm doing the integral of sine of pi times x minus the quantity x to the third minus 4x. And then it's dx. Perfect. And then I'll hit enter, and we'll see what it ends up giving me. The answer is 4. Okay, here we are continuing with problem, the AP Calculus BC 2008 problem number 1. We're on part B. Part B is still asking us to deal with this situation where we have these two functions, sine of pi x and x cubed minus 4x. But in this part we're doing something kind of interesting, maybe. So we're going to consider the line y equals negative 2. If I consider the line y equals negative 2, that kind of chops this area, chops this region, which I was calling R in the previous part, into two regions. And what this wants us to figure out in this next part, in part B, is it wants us to find the area of this region down here, which I'll call S. to distinguish it from the other one. So we're trying to find region S. Now it actually says set up but don't evaluate the integral, and so that's what we're going to end up doing. I think I'll just also evaluate the integral because why not? It's not a hard thing to do, but it's certainly not necessary. So here we are with part B. So again, what I would like to do is I like to think about what x's I can pick in this region and what would a rectangle end up looking like. So first of all, I note that my x's, I'm not allowed to just pick any x anymore. The first x I can pick is right there, and the last x I can pick is right there. And I'm allowed to pick any x that I want in that region, and if I do, let's say that I pick this x right here, then the rectangle that I'm going to end up making is going to be this one. Whoop, like so. On the other hand, if I picked an x over here, the rectangle I would end up making is this one right here. Cool, so I can see what my top and my bottom function are. I can see what the height of my rectangle is at all of these points. So I think the only thing left to do is maybe we can just label these points right here. So maybe I can call this point A and I can call this point B. I'll be solving for them in my calculator. But the area of S is clearly equal to the integral. X is allowed to go from A up to B. And then the height of my rectangle is, well, the top of it is at -2. And the bottom of my rectangle is this function right here, so minus x cubed minus 4x. That would literally be this height, the top number minus the bottom number. Even though they're both negative, it doesn't matter. The top one is less negative than the top one, than the bottom one, so this is going to end up being a positive number, which is the height of my rectangle. And then that gets multiplied by the width of each one of these rectangles, which is a delta x that becomes dx. And so ultimately, this is the integral that I need to solve. Now, in order to do that, I'm going to have to do a couple of things. I'm going to have to figure out what a and b are, and I'm going to do that in my calculator. And I'm also going to end up computing the integral. And I'm going to show you, hopefully with the calculator, what some of the things that I would do. So to find a and b, I think the easiest way is I'm actually going to put the functions I'm interested in, into the calculator, into y equals. So in y1, I'm going to put x cubed minus 4x. X cubed minus 4x. In the bottom function, I'm going to put -2. And then I'm going to quit out of there. I know what my window should be, so I'm going to go ahead and set my window. My x min is 0. My x max is 2. My x scale is 1. My y min is let's say -4. It seems like, and my y max is 0. Should do the job, and I'll hit graph. And when I do that, I nicely see the curves that we have in question. Right now it's drawing the x cubed function, and there goes the y equals -2. So now what I'm going to do is I'm going to calculate. So second, calculate the intersection points. It's going to ask me what's the first curve, what's the second curve, and then it's going to ask me for a guess. It gives me the guess because it's going to try to hone in on the right answer, on the right intersection point, because there are 2. But it looks like x equals, the A point is 0.5, it's hard to see with all the 539188887. And then to find b, I just repeat this process. So intersection, bottom curve, first curve, second curve, guess. This time I might have to guess much closer to the b point. And if I do that, I find out that it appears that this happens at 1.67513. Can't see any of this, it's so hard. 6751309. Perfect. And so honestly, this is the answer to this problem, and I would, you could stop right now, you say this, you say what these 2 points are. I don't even think you have to go to this many decimal places. I think 3 is the standard. Don't quote me on that, it's either 3 or 4 decimal places is the standard. But there you go. I'm actually going to calculate it because why the heck not? So, math 9, and this time I'm going from 0.53918887 up to 1.6751309, and the function we're doing is parentheses -2 minus parentheses x cubed minus 4x. Dx. Hit enter, and I get that the answer is approximately 0.8114, that's good enough, 257963. So this is unnecessary, but that's the answer to this problem. Here we are with 2008 number 1, continuing on to part C of this problem. Now, I've redrawn this picture and it looks kind of weird the way I've drawn it. I've drawn it so that the x and y axes, the idea here is that it's kind of tilted down because this is going to be a volume problem. We've still got this region R, which is the region that's bounded by sine of pi x and x cubed minus 4x. So R is still hanging out there and you can see what's going on. But this time we're going to do something interesting. At every possible x value that I could take, if I go perpendicular to that x value, we're going to imagine creating a square that pops up perpendicular to the xy plane here. So I'm kind of think of the xy plane as kind of like laying down on the ground, and if you do, a square is going to pop up right here, and this is meant to be a square. So its height should be the same as its width. And we're going to do this at every point. So like if I go parallel to the x-axis right here, then there's going to be a little square that pops up. This one's going to be a little bit shorter because the base is a little bit shorter. But there's a little square that's popping up. If I grabbed it right here, there's a tiny little square that's going to pop up right here because the base is really, really small. There's a tiny little square. If I picked my x very close to the x-axis here, there would be a tiny little square that would pop up. And what we're asked to do is sort of imagine the volume of this shape that we would end up getting if we made this thing. And what we're being asked to do is compute that volume. So what I like to do is actually kind of draw a picture like this. And again, I like to imagine picking a particular x value and seeing what the shape is that I would be working with. So if I picked this x value right here, I wouldn't be working with a rectangle anymore, but I'd be working with this like rectangular prism that would pop up like this, and it would have some, part of its width would be delta x, and its height and base are sort of what I'm interested in. So the width is delta x. What does the area of this thing end up equaling? And if I can figure that out, this will end up telling me what the volume is. And I can figure that out. So you should be able to tell that no matter where I pick x, the base of this rectangular prism that I'm making here, the base has a width that is the top function sine of pi x minus the bottom function. Then that also becomes the height of my rectangular prism with the width of delta x. In other words, this distance right here is sine of pi x minus x cubed minus 4x. And that's exactly what this height is as well. Sine of pi x minus x cubed minus 4x. And of course, the width, this little part right here, that's just a delta x, which becomes a dx when we take the integral. So therefore, our volume is, the x's are allowed to range all the way from 0 up to 2. the area that I'm doing, the volume that I'm adding all of these little volumes up. Well, the volume is the area of this rectangle, which is sine of pi x minus x cubed minus 4x, all of that squared, times delta x, which becomes a dx. And so this is the integral we need to compute. So let's do it. We've got a calculator. So I go to Math 9, and I'm doing the integral from 0 to 2 of the quantity sine of pi x minus the quantity x to the third minus 4x. That entire quantity is squared dx. And I come out, it takes it a little while, but I end up getting that the answer is approximately 9.978. Approximately 9.978. And this time these would be cubic units. We don't have units here, but this would be units cubed. It is, after all, a volume problem. Okay, so here we are with the final part of problem number 1 from the 2008 AP Calculus BC exam. I've tried to do my best to draw a good artist rendering of what it is that you're finding here. I don't think that this is absolutely necessary to be able to draw this. I think it's helpful to be able to think about what it is that you're finding the volume of. I find it very helpful when I'm drawing these things, as you'll see, to figure out what the integral that I'm supposed to do is. So we're back to this problem where I've tried to draw what's happening. The xy plane is up here at the top, and we've got sine of pi x right here. And then right here, we have x cubed minus 4x. And now here's what we're told. Basically, this is going to be the shape, that shape that you see here, kind of like a teardrop shape. That teardrop shape is going to be the top of a pool. So imagine I kind of drew this blue line here to represent that this is all water. And now they're going to dig down below this pool in this shape, but they want the depth of the pool to vary with how far it is out on the x-axis. So you're told that however far you are out on the x-axis, if you take a cross-section at that place, the depth of the water at that cross-section, the depth, is always equal to, 3 minus whatever x is. So for example, here we are, here's x equals 2. The depth of the pool at x equals 2 is 3 minus 2, which is 1 foot. On the other hand, at x equals 0, the depth of the pool is 3. So this orange line that I've kind of drawn here that's kind of going down, this is sort of where the bottom of the pool would be, and it's kind of sloping down like this. And at every x value, for example, this x value right here, the depth of the pool is going to be whatever that x value is. You're going to plug that into this equation right here. So the depth of the pool right there is 3 minus x. And our goal, as you probably would expect, is to find the volume of the water that's in the pool. So here we go. Basically, I'm going to do the same thing from before. I'm going to imagine this x value, and I'm going to imagine a little representative rectangle that I might make at this x value that's right here. That little rectangle would look like this. And then that little rectangle would turn into this little prism of water that's going down like this. And I would be interested in the volume of that little prism of water. And that volume ends up being, well, the depth of the water is 3 minus x, whatever x is. And that's the depth of the water. And the width of the water, like how far it is the good old sine of pi x minus x cubed plus minus x cubed minus 4x. Pi x minus x cubed minus 4x. And then, of course, the little delta x, which becomes a dx, is right there, and I'm integrating from 0 to 2. And so this is going to end up telling us the volume of the water in the pool, which I'll now calculate in my calculator. So here we go. I'm going to basically do what we did from before, 0 to 2. But this time I'm multiplying all of that by 3 minus x. And parentheses, and then I'll hit enter. And this time I'm getting a volume of 8.369. It's 8.370 actually, so I think this is approximately 8.370. And this, I think, would, let's see, the actual units here we'll be able to do, I think, this time. Let's see. Actually, they don't tell us what the unit is, but I would expect that this would be something like cubic feet or something, feet cubed of water is what this would end up being.